today we will investigate X-ray matter interaction. So there are many mechanisms related to the X-ray matter interaction, and they depend on many parameters. So today we will learn all these things. Here we have incoming X-rays, incident X-ray beam, okay? It is coming from X-ray tube, or it is coming from synchrotron light source, or it is coming from free electron laser. It doesn't matter. Here we have an X-ray beam. And then here we have a material, okay? It can be ultra thin film, it can be thin film, it can be a bulk material. So you have a material here. So what kind of interactions can be present between X-rays and matter here? So we have three main mechanisms. One is scattering, okay? It can be elastic or inelastic. And we have absorption, and we will investigate absorption in three mechanisms: photoelectrons, Auger electrons, and also fluorescence X-rays. These are the absorption products. And if the material is thin enough, and if the incoming X-rays have enough energies, some parts of the incoming X-rays can pass through the material, and then we can have transmission, okay? So today we will investigate all of them, and depending on the interaction mechanism, scattering, absorption, or transmission, you use them in different methods related to the X-rays. Here we have very important information. So what is the ratio of these interactions? So which one is dominant? Let's say, which percent of the interactions is related to the scattering, which percent is related to the absorption, which percent is related to the transmission. So who decides this? So actually three parameters decide this: X-ray energy, incoming X-ray energy, and the type and thickness of the material here under investigation give us idea about the ratio of the interactions. Now let me start with the absorption. As I told you, here we have within the absorption, we have three mechanisms: photoelectrons, Auger electrons, fluorescence, X-rays. We will start with photoelectrons and photoelectric effect. So what is photoelectron? What is photoelectric effect? It was first observed by Heinrich Hertz in 1887, and then explained by Albert Einstein in 1905. And then, due to this explanation, Albert Einstein awarded by Nobel Prize in Physics in 1921. The photoelectric effect-based methods are actively used in many technological applications. I will not go into detail within this lecture. I will just explain what is the photoelectron, and then I will continue. Here you see an atom. This is the nucleus, and this is the K shell of the atom, L shell of the atom, M shell, and N shell. And we have electrons on these shells, okay? Here we have an incoming X-ray. It comes from the X-ray tube or synchrotron light source, or from any X-ray source. We have an X-ray with some certain energy, okay? And here we have an electron. According to the Bohr atomic model, it is traveling in a circular orbit with some certain energy, okay? And it has certain binding energy. So if this X-ray, incoming X-ray, has enough energy to take this electron out of the atom, okay, to make it free, okay, then here we have a photoelectron. You can consider that the electron produced by photon, okay, photoelectron. And the energy of the X-ray is transferred to the electron, and electron has some certain kinetic energy here. So this is the photoelectron, and we will use them in many X-ray based methods. So now the second product of the absorption, fluorescence X-rays or characteristic X-rays. So during the first lecture, we have learned that characteristic X-rays discovered by Barkla in 1909, and then due to this discovery, Barkla awarded by Nobel Prize in Physics in 1917. Okay, so what is fluorescence X-rays? Actually, we have discussed this one in the past, but let me shortly discuss again here. Here we have an empty state. So let's consider that at the beginning there was an electron here, and then you send an X-ray, and then you remove this electron from this energy level, and another electron from the outer shells, from this one or from this one, drops here. Then here you have a delta E, energy of the upper level, energy of this empty level. Okay, here we have delta E. So this delta E is used to produce an X-ray. Okay, this is fluorescence or characteristic X-ray. Why characteristic? Because delta E for each element is unique for this reason, characteristic. So I am repeating, there is an X-ray which is coming from the synchrotron light source or from an X-ray tube, and then here you have an electron. This X-ray removes this electron from this energy level. Let's consider you produce photoelectron, and then here there is an empty state. Okay, and then from outer shells one electron drops here, and here we have delta E, energy difference between these two shells. Okay, so this delta E is converted to produce an X-ray. So this is fluorescence X-ray. So this also has many applications and very important also for industrial applications. And we will also see some scientific applications. Now let me finish the absorption with Auger electrons, which is independently discovered by Lisa Meitner in 1922 and Pierre-Victor Auger in 1923. So again, let's consider that X-ray is coming and then interact with this electron. It has enough energy, and then this electron becomes photoelectron or free electron, or it is excited, let's say. Okay, and then from the outer shells, one electron drops into this level, and then here we have delta E. Here in the fluorescence X-rays case, I have told you that this delta E is converted to an X-ray, fluorescence X-ray, but with very less percentage. This delta E can be transferred to the outer shell electrons here. Okay, so this delta E energy difference can be transferred to the outer shell electrons, and if this delta E is bigger than the binding energy of this outer electron, then this electron can be free. Okay, these are the Auger electrons. This is the difference between fluorescence X-rays and Auger electrons. This delta E is to produce fluorescence X-rays, or it can be transferred to the outer shell electrons. It depends on the element, okay? The percentage of this fluorescence X-rays and Auger electrons. Do you have any question here?
No.
Now, let me tell you what kind of methods used based on the absorption mechanism. We have X-ray absorption spectroscopy based on the absorption, and there is X-ray magnetic circular dichroism. It is also another absorption-based experiment. And the other one is X-ray photoelectron emission microscopy, XPEM, okay, short name, or XMCD-PEM. Another absorption-based method is X-ray resonant magnetic scattering. And the last one is X-ray fluorescence, okay? So these are the absorption-based methods, and very important for scientific purposes and technological applications. I will discuss in detail these 4 methods, and I will only show you the applications of this XRF method in historical paintings and also in archaeological objects. So now let me continue with the scattering mechanism. We have two main scattering. One is elastic scattering, the other one is inelastic scattering. So what is the difference in between? In elastic scattering, the energy of incident photon is conserved, but its direction of propagation is modified. So let me draw here. Let's consider that here there is an electron, okay? And then one X-ray comes with some certain energy, let's say E1, and wavelength is lambda 1, okay? This X-ray interacts with electron and then scattered in different direction, and final energy of this X-ray photon and the final wavelength of this X-ray is same as the initial energy and wavelength. So this is the elastic scattering, okay? You may already know from your previous lectures. So here we have two types of elastic scattering. One is Thomson scattering, which is the elastic scattering of electromagnetic radiation by a charged particle. Here in our case, electromagnetic radiation is X-ray and charged particle is electron in the atom, okay? Thomson also awarded by Nobel Prize in 1906 due to the discovery of electron. And what about the Rayleigh scattering? Rayleigh scattering is also elastic scattering of electromagnetic radiation by particles much smaller than the wavelength of the radiation. So let's consider that you have X-ray as an electromagnetic radiation and it has certain wavelength, and these X-rays interact with the electrons in the atom, which have much smaller size compared to the wavelength of the X-ray. So this is Rayleigh scattering, and Lord Rayleigh discovered this Rayleigh scattering, and he was also awarded by Nobel Prize in 1904 due to his discovery of argon element. So then let me discuss the inelastic scattering. In inelastic scattering, both the energy and momentum of the scattered photon change. So energy and momentum of the scattered photon is not conserved, okay? So of course, the total energy of the system is conserved, but we are talking about the energy and momentum of the scattered photon. I will go into detail a little bit related to this inelastic scattering. Compton scattering is an example of inelastic scattering. So Compton also awarded by Nobel Prize in Physics in 1927. So here, before I go into detail related to the Compton scattering, I would like to repeat here again that who dealt with X-rays at the beginning of 20th century discovered very nice things and findings in physics, also in chemistry, and awarded by Nobel Prize. Now let me continue with the Compton scattering and explain a little bit in detail. Here we have an incident photon. It comes with some certain initial wavelength and initial energy. And here just consider that we have an electron, it is at rest, okay? So this X-ray is coming, let's say, along the X direction, and after the collision, this electron is recoiled in this direction and the X-ray is scattered in this direction. But the main difference between the elastic scattering and inelastic scattering, after the scattering, the wavelength and energy of the scattered photon is changed, okay? So this has initial wavelength and initial energy. Now we have final wavelength and final energy. So some part of the energy is transferred to the recoiled electron. So this is the Compton scattering. But in case of elastic scattering, the energy of the incident photon and the energy of the scattered photon are same. In Compton scattering, we have a different wavelength and energy of the scattered photon. So what do you see here? At the beginning, this photon has certain energy and momentum, right? And at the beginning, this electron has no momentum. And after the interaction between photon and electron, this electron has certain momentum and it has components along the x-axis and also along the y-axis. So what do you see here? This photon has also components along the x-axis and y-axis after scattering. So now let's apply the conservation of momentum parallel to the propagation direction of the incident photon and then perpendicular to the propagation direction of the incident photon. So this is the first case, parallel to the propagation direction of the incident photon. So what is the momentum of the light? Momentum of the incident photon is given by h over lambda. This is Planck's constant. This is the wavelength of the incident photon. Lambda or lambda initial, you can say. And what is the momentum of the electron here before the collision? Momentum of the electron is 0 because it is at rest. So we have nothing else here. And on the right side, after the collision, after the interaction, this is before the interaction, this is after the interaction, we have momentum of the scattered photon along the x-axis is given by h over lambda prime or lambda final, let's say, times cosine theta. We are dealing with the component of this momentum of the photon along the x-axis plus momentum of electron times cosine phi. So we are dealing with its component along the x-axis. Okay, so momentum conservation along the x-axis. So now let's apply the momentum conservation along the y-axis. So what is the momentum of the photon at the beginning? It is 0, okay, because it is traveling along the x-axis. And then what is the momentum of the electron? It is also 0. So on the right side, we have momentum of the photon along the x-axis, which is given by h over lambda prime sinus theta, plus momentum of the electron along the y-axis, which is given by momentum of electron times sinus phi. So now I have two equations, and I got these two equations by using conservation of momentum. And now we will apply conservation of energy, and we will use the previous equations. So what about the conservation of energy? So energy of the total system before the collision or before the scattering, and energy of the total system after the collision. So what is the initial energy of the incident photon, which is given by hc over lambda initial wavelength, Planck's constant again, velocity of light, plus the electron is at rest, but it has certain energy, right? We know this information from the particle physics, and this energy of the electron is given by mc square, mass of the electron and square of the velocity of light. And after the collision, we have energy of the photon, which is given by hc over lambda prime. So actually, these are the energies, right? Initial energy of the photon, final energy of the photon. And here we have final energy of the recoil electron, which is given by p squared times c squared. This is momentum of the electron, and me squared times c power 4, or let's say square root of this term. So this is the final energy of the electron. I will not go into detail to calculate this one because you already done this calculations in nuclear and particle physics. So now if I use this equation, and if I use this equation, then I can get this final equation, which defines the Compton scattering what we have here, this is the lambda prime. Final wavelength of the scattered photon is equal to lambda initial wavelength of the incident photon plus Planck constant over mc times 1 minus cosine theta. So what do you see here? This Planck's constant is constant. Mass of electron is also constant. And velocity of light is also constant. So here we only have constant numbers and parameters. And what is lambda? This is the initial wavelength. I know this initial wavelength, right? Because I sent X-rays from the X-ray source. I know the wavelength. So finally, I would like to measure the energy of the scattered photon, or I would like to determine the wavelength of the scattered photon. So what to do? If I know this theta angle here, then I can easily calculate the wavelength of the scattered photon. So X-ray based Compton scattering experiments use this formula, okay, in order to find the final energy of the scattered photon. Do you have any question here?
No, it's clear.
Okay. Then what about methods? And within the scope of this course, during this semester, I will explain what is X-ray diffraction, and I will also spend some time to teach you X-ray diffraction based methods and also applications. And we will also learn X-ray reflectivity. Small angle X-ray scattering is also a scattering method, and the other one is inelastic X-ray scattering. So I will spend many time with X-ray diffraction and X-ray reflectivity. These are also widely used in laboratory X-ray machines for many different fields of science. So these two methods are very important. So I will spend a lot of time for these two methods. And now let's discuss the interaction of X-ray with an atom. Just consider that you have an X-ray beam and many X-rays within this X-ray beam. And this beam comes to an atom, okay, just single atom. So how to write this interaction with a mathematical formula? It is described by the complex amplitude. So this is the complex amplitude. It depends on the angle and also energy of the incoming X-rays, okay? So here we have a subscript T depends on the theta. What is this? This is Thomson scattering amplitude. And here we have F1 plus I F2. So what is F1? What is F2? Both F1 and F2 are atomic scattering factors. F1 defines total scattering mechanisms, and F2 defines total absorption mechanisms, okay? Actually, if you are dealing with X-rays or if you are dealing with optics, if you see here I, imaginary number, okay, then it means that this term is related to the absorption. Imaginary part in optics is related to the absorption. And here we have a real part which is related to the scattering, okay? So this is atomic scattering factor for total scattering, and this is the atomic scattering factor for the absorption of X-rays. And this is the Thomson scattering amplitude, which is the interaction between X-ray and a single electron, let's say. And so finally, we have complex amplitude, which defines the interaction of an X-ray beam with an atom. But in reality, we are dealing with materials, and within these materials, there are millions or billions of atoms, okay, many atoms. So what about the interaction of X-rays with a matter? So the interaction of X-rays with a material is described by complex refractive index, which is given here. This is the N complex refractive index equal to 1 minus delta minus I beta. So as I told you, imaginary part is related to the absorption and real part is related to the scattering. This is the delta scattering index and this is the beta absorption index. Okay, this is the complex refractive index. So here we have delta and beta, which are used to define scattering and absorption. Okay, here we have F1 and F2, which are used to define scattering and absorption respectively, right? So there must be a relation in between F1 and delta, between F2 and beta. We should have a relation, right? So how to write this relation? We can write this relation by using this K constant. So what we have here, delta is equal to K times F1, beta is equal to K times F2. So what is the K? K is given by classical electron radius times lambda square, the wavelength of the incident X-rays, over 2 pi times Avogadro's number times density over atomic weight. So what do you see here? This is constant for certain material. This is constant. This is constant for certain material. This number is constant. This is constant. And also if you keep the incident wavelength constant, this is also constant. So here we have a constant number K, okay? So, and we have relation between delta and F1, beta and F2. Delta is scattering index. F1 is atomic scattering factor for scattering mechanisms. Beta is absorption index. And F2 is atomic scattering factor for absorption of X-rays. Do you have any question here related to this part, interaction of X-rays with matter? Now let me continue with the transmission, how to define transmission. So what is the meaning of transmission? Let me first of all draw a sketch here. So let's consider that here we have a material and this material has certain thickness of T. And here we have an X-ray beam with some certain intensity and with some certain amplitude. Let's say we have many X-rays. After passing through this thickness of the material, we have less X-rays, okay? This is the final intensity and final amplitude A. This was the initial intensity, initial amplitude A0, okay? So the amplitude and intensity of the X-ray beam passing through a material of thickness T is given as follows. What do you see here? The final amplitude A is given by A0 times E over minus 2 pi beta times T over lambda times E over I 2 pi delta T over lambda. What do you see here? We have beta T lambda, delta T lambda. So beta depends on the material, okay? Delta depends on the material. And T in Bohl's exponential term gives us the thickness of the material, and lambda is the wavelength of the incoming X-rays, okay? So this is the amplitude of the X-rays after passing through this material with the thickness of T. So what about the intensity of these X-rays? Intensity of the X-rays after passing through this material is given by I, which is equal to I0 initial intensity times E over minus 4 pi beta times T over lambda. Here we have absorption coefficient times thickness and over lambda. So what do you see here? Lambda is the initial wavelength of the X-rays, beta depends on the material, and T is the thickness of the material. So instead of 4 pi beta over lambda here. Let me use the pen. So here we have this term. So instead of this one, we use this term mu, linear absorption coefficient. Okay. So this linear absorption coefficient depends on the material because beta is characteristic for every material and depends on the wavelength of the incident photons. So this is the linear absorption coefficient. So by using this mu instead of this term here, finally I can get intensity relation. So now we have final intensity, which is equal to initial intensity times E over minus mu T. This is the thickness of the material. This is the linear absorption coefficient of the material. Do you have any question here? Let me show you the meaning of this equation. Here we have this material. Let's say this is the thickness of the material. This is the time, and this is the intensity. This is the I0, initial intensity. So before the material here, with the thickness of T, we have intensity of photons with I0. Okay. Whenever they enter into this material with this relation, look at this one, E over minus mu T. Okay. So what is this one? E over minus mu T. So this is this kind of decrease, right? So then intensity of the X-rays decrease with this relation within the material, and we have the final intensity here. This is the I, final intensity. Okay, so intensity drops here with this relation within the material, and depending on the thickness and depending on the linear absorption coefficient, this drop can be very high or lower. Okay, let me also discuss this point. So let's consider that you have material with higher mu. Then it will be like this. Okay, if the linear absorption coefficient of the material is higher, then the intensity will drop faster. So, for example, you would like to use shielding materials in X-ray diffraction machines or also in the röntgen rooms in the hospitals. So what kind of material you have to use as a wall or shielding material? Then you have to choose the material with the highest mu, okay? For example, we are using lead. Lead has very high mu value for X-rays, and then they can easily stop X-rays with very small thicknesses of the lead material, okay? Or if you don't have material with higher mu, then you can increase the thickness here, then you can also decrease the intensity. So let's consider here in second case, you have a thicker material. Now thickness is much higher. So now let's discuss the first situation. This was the initial situation with smaller thickness, and now we have much thicker material. Then it continues to drop. Okay, now you have final intensity. So this term is very important in transmission experiments. So let me also tell you here that within the forthcoming chapters, within the forthcoming parts of this course, this information, this relation will be very useful, and please always keep this formula in your mind, okay? Final intensity is equal to initial intensity times E over minus mu T. In some books, you can see instead of T, thickness here, you can see D, okay? So you can see this type of definitions. I0 E over minus mu D, or I0 E over mu x, okay? You can see this type of definitions and symbols for the thickness of the material, but they are defining the same thing, okay? This is the thickness of the material. Any question here? Then let me continue with the transmission methods. So we have explained the transmission, and at the beginning of my lecture, what I have told you that the interaction mechanisms, scattering, absorption, and transmission depend on the X-ray energy, type, and thickness of the material. What do you see here? Here we have thickness, and mu depends on the type of the material. And within mu, what we have lambda, right? So energy of the X-rays are also given here, okay? And they affect the interaction mechanisms. So now let me show you the transmission methods. So the most common one is the Röntgen imaging. It is used in hospitals for medical purposes, computed tomography, which is also used for medical purposes, but also for the industrial applications and also for security applications in customs. And what else? X-ray magnetic circular dichroism with transmission method. I will discuss this one at the end of this semester. So these are the transmission-based methods. Now, let's discuss the effect of X-ray energy on interactions. So here I have told you that the X-ray energy, the type and thickness of a material affect the ratio of the interactions here between X-rays and matter. So we have discussed the type and thickness of the material. Now let's go into detail with the X-ray energy. Here I have X-rays with different energies, and then I will explain which one is useful for which applications. So let me start with the soft X-rays. Soft X-ray means that low energy X-rays, okay? So we define as energy of the X-rays is lower than 2 kiloelectron volt. And what we have, what are the interaction mechanisms? What about the scattering? What about the absorption? What about the transmission with the soft X-rays? So soft X-rays have lower energies than the 2 kiloelectron volt. So then the elastic scattering is less than 1%. Inelastic scattering can be neglected, okay? So scattering can be neglected, okay, if you are using soft X-rays. And the photoelectric absorption is dominant. So if you are using soft X-rays, you can carry out absorption experiments, okay? Why? Because many element has K, L2, and L3 absorption energies around this range, lower than 2 kiloelectron volt. Later on, I will go into detail and I will give you many examples, okay? So since the KL absorption energies of many materials are in this energy region, low energy X-rays or soft X-rays are used for techniques such as XAS, XMCD, XMCD-PEAM, and XRMS. All of them are absorption methods, okay? So you are dealing with photoelectric absorption mainly. Of course, within these methods, you can also use fluorescence X-rays, which is also another absorption product, okay? But the mechanism is mainly dominant with photoelectric absorption. Do you have any question here related to soft X-rays?
No, thanks. It's clear.
So now I changed the energy of the X-rays. We are discussing the effect of X-ray energy on interactions. So what happens if I use X-ray energies higher than 2 kiloelectron volt? For example, for the X-ray tubes, we are mainly using copper K alpha radiation. The energy is around 8 kiloelectron volt, okay? So huge energy compared to the soft X-rays. So what happens if you use hard X-rays? So scattering becomes much more important. Here, in case of soft X-rays, absorption is dominant, but in case of hard X-rays, scattering is dominant, okay? Because as the energy of the incoming X-rays increases, if you are using highly energetic X-rays, the absorption cross-section decreases more than the scattering cross-section. So absorption can be neglected here. So then if you would like to carry out scattering experiments, you have to use hard X-rays. Why? We are talking about very energetic X-rays. Energy is higher than 2 kiloelectron volt. For example, let's discuss the copper K alpha radiation. So the energy of the copper K alpha radiation is 8048 electron volt, 8 kilo electron volt, let's say, okay? And the wavelength of this energy is 1.54 angstrom. You can calculate this one by using this relation. E is equal to hc over lambda, okay? And then you can get this lambda for the copper K alpha radiation. What do you see here? Wavelength of the incoming X-rays are around the atomic distances, right? Around 1.5 angstrom, 2 angstrom. So then you can carry out diffraction experiments. We will go into detail later on. In addition to that, this medical imaging, industrial imaging, and security applications in the customs, in the shopping centers are related to the transmission, okay? You have to transmit X-rays from the material. So if the energy of the X-rays are not enough, then they will be absorbed within the material and you will not have something. Let me draw here. Let's consider here you have a material and here you send an X-ray. This is the energy of the X-ray. And here you have a detector, okay? This material is thick and it has certain mu absorption coefficient, okay? If the energy is high enough, these X-rays can penetrate deep into this material and they can pass through this material and they can reach to the detector. If the energy is less and then they are absorbed here, scattered here, and then we have nothing after the material. For this reason, for medical applications, for Röntgen imaging, for industrial applications, for the computed tomography, for example, for industrial applications, you are investigating the metals or plastic, okay, very bulky materials, so you need hard X-rays, and also for the security applications. So with this one, I have finished my lecture today. This was shorter lecture, but very important for the forthcoming chapters, because in the forthcoming chapters, we will discuss X-ray detectors and you have to know the X-ray matter interaction in order to understand the mechanism of the X-ray detectors. In addition, we will discuss X-ray diffraction, X-ray reflectivity, and many absorption-based X-ray methods and many imaging methods. So for all this type of applications, you have to know the information on the interaction of X-rays with matter. You have to know the scattering mechanisms, you have to know the absorption mechanisms, and you also have to know the transmission. Do you have any question?
No, Hocam, thanks.
Then see you on Wednesday. Bye-bye.
See you, bye.